So now we're looking at linear system with three unknowns. And this is a system that would look like this if it has three equations. So we're going to look at three equations, three unknowns. But we can draw similar conclusions and results if we add a fourth equation or just have two equations. Okay, so three equations, three unknowns. Let's look at the different cases that we can have. First case is you have three parallel planes that are not overlapping, so no common intersection. So I'll try to draw some parallel with the case where you have two equations, two unknowns. So two equations, two unknowns. The case that resembles this one is when you have two parallel lines that are not identical, so not overlapping, and in that case you have no solutions. So there are no points that are part of the three planes at the same time. And the second example here, the second case, is where you have two parallel planes and one that's cutting through them. So with two variables, you'd have like two lines that are parallel, one cutting through them. In this case, there aren't two solutions here because you don't have a point that's part of all three lines. Well, same case here. You don't have a point that's part of all three planes at the same time. Okay, doesn't happen. You've got points that are part of, let's say, the first and the second plane, or the first and the third, but not all three at the same time. So no solutions here. Here, you're in a situation where you'd have like lines, I don't know, like that. So you have intersection points, but none of them actually belongs to all three lines. So same thing here. You have planes that are intersecting, but no common intersection point. So no solution. Here you have two overlapping, you say the analogy, you have two overlapping lines and one that's non-overlapping, but in this case you have no solutions. Well, here, same thing, two overlapping planes, but one that's parallel, non-overlapping, no common intersection points. And maybe coming back to one, I should have drawn, this is what I should have done. The analogy with one would have been something with three parallel lines. Okay, so all situations 1, 2, 3, and 4 have no solution. So let's move on to the next case. Here we go. So in this situation, you've got three planes intersecting, and you've got a common intersection point. Notice that here they intersect at a right angle, but they don't need to. You could have planes that intersect and that are not orthogonal to each other. So this is the case where you have a unique solution. So I guess the analogy with two lines would be, I can't draw three lines here. With two lines you'd have something like this. If you want three lines, it'd be like that. Okay, but a common intersection point. So this is case number 5. Case number 6, you have planes that are intersecting along a line like this. Okay. I don't think I can draw here a good analogy in two space. So we'll have to stick to 3 space here. So here you have infinitely many solutions because all the points here on the line, they actually are part of all 3 planes. So it's part of the solution set, and you have infinitely many points in that solution set. So infinitely many solutions to the linear system. Case 7 is where you have all planes overlapping. So every time you've got, by the way, a plane that's overlapping with another one, it's because you've got two equations that are essentially identical. They're identical up to a constant multiple. So you could have like one equation that's, I don't know, 2x plus 4y plus z equals 1. And the other, maybe that's like 4 times this one. So I don't know, 8x plus 16y plus 4z equals 4. So although they could kind of look different, they're not, right? It's actually the exact same equation. So you've got the same plane. So this is how you get overlapping planes. So in situation 7, all three planes are identical. So all three equations are up to a multiple. The constant, the exact same plane. Here you've got in 8 two overlapping and one that's non-overlapping, so they intersect along a line. So you've got again infinitely many. So you'll notice that in all cases you either have no solutions, one solution, a unique solution, or infinitely many. So this is similar to the situation where we had linear systems in our that were lines in R2, so two variables. And this is why you have this theorem that you should actually write down in your notes. Every system, it's actually true for R3 and R2, but also it's good for a linear system that's done in a higher space. So if you have like more than 3 variables, it's still correct. Every linear system, no matter how many equations or how many variables you have, either have 0, 1, or infinitely many solutions, and there are no other possibilities. Which actually means that if you've got 2 solutions, automatically you've got infinitely many. Okay, if you have 2, you can construct more than you can construct a third one that's different, and a fourth one, and a fifth one. So you're going to have infinitely many. I've recopied the theorem that you have in the book. You should write that down in your notes. And I've added also the sentence, as soon as there are 2 solutions, there are infinitely many of them. And the proof is yet to come. Okay, so we're not ready to give an algebraic proof of that. So later, we'll do that later. Not later in that section, later later in this chapter maybe. I want to look at an example, one equation and maybe 3 unknowns. So this is the most basic linear system. You just have one equation. It's not really even a system, it's just an equation. And I want to show you how you can maybe recover the solution set. Actually, we'll do that in the next video. Maybe here I'll just talk about what that equation represents. Well, it's an equation of the form ax plus by plus cz equals 5, right? So these equations, they represent a plane, right? In R3, we can easily recover the normal vector, the vector that's perpendicular to the plane, right, by collecting the coefficients ABC. So 1 minus 4, 7. So it's perpendicular to 1 minus 4, 7. And maybe to describe that plane, I also need to specify a point that belongs to that plane. So passing through, it's very easy to come up with a point, right? There are infinitely many of them, of course. I like to just assign values to 0 to y and z. You solve for x, and here we go. You've got a point very, very easily. So examples of solutions you have, well, here's one, right? The point that belongs to the plane we just calculated. But there are other ones. I don't know. I could assign a value of 0 to x and z. Solve for y. I would have minus 5 over 4 for y. I could assign values of 0 to x and y and solve for z. And now it's 5 over 7 for z. And I can keep going like this. 910 is also a solution, you see. So, but my point here is, look, as soon as I see 2 solutions, then I know there are going to be infinitely many. Okay, this is what I partly wanted to illustrate. And based on what we have here, we actually know that the solution set's a plane. And how many points you have on a plane? Well, clearly infinitely many, right? You've got points everywhere on that plane. Okay, actually it stretches out in all directions. You've got infinitely many points, so infinitely many solutions to the equation. Okay, so next video we're going to look at how we could recover the solution set of an equation like that.